Welcome back to the course Modeling Combustion with Answers Fluent offered by Adult Systems. In today's class, we will discuss about non-premixed combustion model. So let's begin the class. So what is non-premixed combustion model? So this model is used to simulate non-premixed combustion flows where it is completely based on a conservative scalar approach. This is because all the thermochemistry is reduced to a single parameter, that is mixture fraction. So this mixture fraction is nothing but a local mass fraction of the burnt and unburnt fuel stream elements like carbon and hydrogen present in all the species like carbon dioxide, water, O2, etc. So when we are using this mixture fraction approach, there is no chemical source term present in the governing conservative equations which we defined earlier, that is the species equations, and so the problem simplifies to a simple mixing problem. Also in this model, probability density function, that is a lookup table, is used where the fluctuating mixture fraction can be completely defined. So we will get to know what is this PDF or the lookup table and how we calculate it and how we incorporate it in the simulation. So some of the key features of this model are, based on our problem, we can define 5 different state relations. It may be chemical equilibrium, it may be any flamelet model, etc. Also based on our problem, we can define what energy treatment the problem is dealing with, that is adiabatic or non-adiabatic. As I said about the mixture fraction, we can define a single mixture fraction problem or 2 mixture fraction problem where 2 fuel inlet streams are present. Next is the probability density function or the lookup table. Also in this model, like species transport, rigorous turbulence chemistry interaction has been taken care of. So some of the limitations of this model are that it cannot be used for compressible or non-turbulent flows, and also it is not applicable for pre-mixed systems. So now we'll see the steps involved in modeling non-premixed combustion model. So these are the complete 7 steps which we will go through detail one by one, and we'll understand how these steps help us in defining the non-premixed combustion model. So the first step, we will be defining the type of chemical description of the problem. After enabling the energy equation and the turbulence equation, we have to go into species, and then we have to enable non-premixed combustion model. Then we have to define the state relation and the energy treatment. So state relation out of the 5 and energy treatment out of the 2. Then we have to define if there is any secondary inlet stream. Also we can enable the rich flammability limit in this model, and we can also allow coal calculation. We also have to specify operating pressure for the system. So after defining all these terms, we will go to the second tab, that is the boundary tab. In this boundary tab, we have to define boundary species for the streams in the reacting system model. That is what fuel and what oxidizer will be in our system, and in what mole fraction or mass fraction it will be present, with what temperatures. We have to define all these things in this boundary. Next tab we will go, which will be the control parameters. So in this tab we can control what all species should take part and what all species should be excluded out of the system. Likewise, one example is that NOx species we can exclude from the equilibrium calculation using this control tab. So the next step is calculating the lookup table. So now everything has been defined, what all fuel oxidizer species and their mass fractions will be present. Now we will go and we will calculate the lookup table. So here automated grid refinement is one option which we have to enable. That is based on our mesh, it will take particular points and it will calculate the variance or the variation of the mixture fraction from one grid point to another grid point. This all process will happen behind, and we will get an output file, that is a PDF file, which we can export it and later we can import it during our calculation. One can also disable the automated grid refinement option, and then they can provide each and every term as it is present in the dialog box, and then they can calculate the lookup table. So the next step, defining boundary conditions. So earlier we have defined the mass fraction or the mole fraction in the boundary species. Now when we are defining for our surfaces the boundary conditions, then we have to define mean mixture fraction and mixture fraction variance. We have to specify this at our inlet boundaries, and it is very necessary to define because these are the 2 terms which will be calculated along with other governing equations. In some cases there will be diffusion problem also, so even that option is present in this model, then we can use inlet mixture fraction diffusion. So the next step is solution strategies for non-premixed combustion. So after defining everything, when we are about to start the simulation, it may happen that the solution won't converge and it may start diverging. This is because when we are dealing with the combustion calculation, there are large changes in temperature which will cause change in density, which in turn can cause instabilities in the flow solution. So there are various strategies one can follow, changing the under relaxation factors, mainly the under relaxation factors of density one can change. Even as a fluent sometimes recommend to change the value of default 1 to the maximum of 0.5. So the next and the last step, that is after finishing everything, the simulation is done, we can generate graphical plots or alphanumerical reports of the following terms. We can calculate or we can see through a 3D plot or graph of these following variables. So here I have added one picture which is showing 3D plot of a lookup table for temperature generated for a simple hydrocarbon system. So the summary for today's class, we have seen that the non-premixed model is completely based on conservative scalar approach because under some assumptions, the thermochemistry is reduced to a single parameter, that is mixture fraction. This model gives 5 chemical states and 2 energy treatments based on other type of the problem. Next, we can calculate the lookup table before the simulation, and then we can incorporate this PDF table or the lookup table in the chemical species calculations once we start the simulation. Next, we have seen that there are some limitations for this model, that it cannot be used for compressible or non-turbulent flows, and then we have studied in detail the steps involved for modeling non-premixed combustion model for reacting combustible flows. So the references for today's class are present here. In next class, we will start with modeling combustion using premixed combustion model. Thank you.